So let's talk about the term entropy. Entropy, in simple word, is a measure of randomness. Okay, random measure of randomness. So we know from previous chapter, according to kinetic theory of gas, the gas molecules are in random motion. Okay, random motion. So what will happen? Let's just see one example. In this beaker, in bucket, we have ice. Okay, this is ice at 0°C. If we supply heat, to the ice, what will happen? That it will convert to water, say at 0°. Okay, if we keep supplying heat, then it could be possible that it could go to higher temperature. Say, for example, this is the water at, say, for example, it is 35°C. So this means if we are going to supply the heat, the randomness of molecules, randomness of molecules, in this case, water molecules increases. So that's how we say that entropy of the system here, entropy of the system increases. Okay, so for example, in ice, the molecules can in ice the molecules of water are generally packed. If you're supplying heat, it converted to water, then these water molecules gets more energy, so that its randomness increases. So we say that entropy of the system increases. Okay. In general, we define the entropy as ds equals dq over t. Okay, this is the equation. So in this equation, this ds represents the change in entropy. Okay, this dq represents, here is the small amount of heat supplied. Small amount of heat supplied. Okay, and here T represents the temperature. We are assuming that temperature remains constant for a small change in a small supply of heat in Kelvin scale. Okay, so this equation is true for say for the reversible process. But we'll see later that this equation can be used if it is not even the process is the reversible. Okay, so from here we can see the unit of entropy is joule per Kelvin. Okay? Joule per Kelvin. This equation further can be simplified as ds integration equals dq over t. Okay, so entropy. So even though we are right, yes, we are talking about the change in entropy. Change in entropy, say this equals dq over t. We are not taking out t from this integration sign because temperature may or may not be constant. So here, this S represents change in entropy. Change in entropy. That's the reason that in some textbook, instead of writing S, they use symbol delta S to represent the change in entropy. So this go from state 1 to the state 2. So 1 represents the initial state, and here 2 represents the final state. Okay, final state of this. So let's take the example 1. Okay, say for example, in this case, I have ice at 0 degrees Celsius. Say its mass is, say for example, 2 kilograms, and we supply the heat so that it converted to water. So you know that mass still remains the same. It is the 2 kilograms, and temperature is just 0 degree. It just ice get melted. So in this case, we want to find what is the change in entropy. So change in entropy, okay, we can find as using the same equation that we have, is we can use dq over T. Okay, so in this case, you see the temperature is constant. So this temperature is constant here, 0 degree. It is also 0 degree. So this T will come out from the equation. So it will be 1 over 273 in the scale of in the Kelvin scale. So we have dq. Okay, so you see that this is the change of state. So change of state. If this is the change of state, we can write the equation as, you know, heat supplied is, in this case, amount of heat supplied is m into a specific latent heat, okay, ml. So L is the latent heat. We can use this equation over here. So this will be 2 times the specific latent heat of ice is roughly 3.3 10 power positive 5 joule per kilogram. Okay, so if you solve that, we can get this much joule per Kelvin. Okay, we can take the similar example. Okay, so in this case, instead of say we have water, say it again mass is the 2 kilogram. Say its temperature is at 0 degree. We supply the heat to the system. Okay, so it is just still at water, and the mass will still be the same. It is the 2 kilogram. Say we convert it to temperature up to, say for example, 80 degrees Celsius. Okay, so we want to find what is the change in entropy in this scenario. So change in entropy will be from dq over T. Here our temperature changes from T1 to is final temperature is T2. Okay, so just we write here our initial temperature is T1. It is 273 Kelvin, and T2 is, you know, 273 plus 80 Kelvin. These are final temperature. So dq here is the change of state. So we can use, you know, before that, in this case, we can use Q as our formula is mc theta. Okay, this kind of equation we can use here. So based on that, we can write 2 kilogram. Okay, 2 kilogram, and a specific heat of water is roughly taken as 4200 joule per kilogram per degree Kelvin or per degree Celsius. Okay, and our change in temperature. Okay, so we have to write because the temperature is going to change, so we have to write dt over t. Okay, once you have this, you can take out this constant from outside and just do the integration, and you'll find something joule per Kelvin. Okay, so these are two examples that gives you brief concept how to find the entropy change. So next we want to say that the entropy depends on initial and final state. Okay, so for example, point A has say state P1 and temperature T1, and B has state P2 V2 and T2. Okay, so system can go from A to B through different route. For example, it can go from A to B through the first path, or the system could go from A to B from second path. Okay, it could be many one. Okay, so either path, for either path, what will happen is that change of entropy will be the same. So in this example, change of entropy from, say, in this example, from A to B will be same for both paths, first and second. So it will not depend on the path. Okay, so one important concept here is that total entropy change for a complete cycle dq over t will be zero for the reversible cyclic process. What is meant by reversible cyclic process? So in this example, if you consider, in this case, say system went from state A to state B, and again back to state A. If this is the case, system started, in this case, the system started with A, went to state B, okay? Then again, it went back to initial state A. So it is a complete cycle. For the complete cycle, it is a total entropy change of the system will be, net change will be zero, okay? So you can write change in entropy for a complete cycle will be zero. So entropy, we can write here, entropy is not a conserved quantity. Okay, for an isolated system, the change in entropy will be greater than or equal to zero. So the second law can be, we can state in this way also, is that change in entropy, in terms of entropy, second law can be stated like that: the entropy of a closed system and the entire universe never decreases. So it will be either zero, or the value could be more than zero. Okay, so it could have anything in between. Let's take the example, like one of the example in the case of free expansion. So we can say this is an example for the this entropy. So if initially V1, you can consider this picture. Okay, in picture A, the gas molecule is confined in a volume V, and this part is empty, completely empty. Okay, so so then the gas go the free expansion, means now this gas molecules occupy the volume V2. So this is we can state that this is the initial state, this is the final state. Okay, so in this case, this is the case of adiabatic free expansion. Okay, so we can find the we can find the what is the entropy change in this case. So if temperature is constant, if temperature will not change, what will happen, that change in internal energy, this will be 0. Okay, so change, this is dq, du represents the change in internal energy. Okay, so now let's say we want to find the how much is the change in entropy in the case of free expansion. Okay, so let's find change in entropy. We can write change in entropy as dq over T. So in this case, temperature is constant, so we can take out T outside from this integration. So this will be dq. So okay, so dq. So we can write that dq as, we know from dq as, let's see, from first law, dq is equal to du plus dw. If we don't have change in internal energy, the total heat supplied, this gives the concept that total heat supplied Q will be exactly equal to the work. Okay, so in the case of isothermal, okay, in the isothermal, we know that this work can be written as, so this is Q over T. So in the case of the isothermal, this work done, this Q can be replaced by W over T. So in the case of isothermal, the work done will be nRT log, final volume is V2 is V1. So this is the work done. This is the work done in isothermal. Okay, so we can write over T, this T and T cancel out. So the change in entropy in the free expansion will be nR log V2 over V1. Okay, so this is the change in entropy in free expansions. So we can say that the randomness means entropy, randomness of gas molecules increases in free expansion. Okay, this is the scenario here. So in this case, we are not talking about this adiabatic. This is the pre-expansion case. So we can use this equation to find the entropy change. Now, based on this, you can practice this question number 5. Okay, and similarly, you can do the other problem is the practice question number 6. These are based on the previous equations for the entropy. Okay, Now let's talk about entropy in the microscopic scale. Okay, so let's start with an example. Say, for example, you have a coin. Say, for a coin, we have head. So I represent S to represent head. Okay, and the other side of the coin we call it tail. Okay, so if you flip it, if you flip it, then either you are getting head or you are getting tail. So you can say it, the probability of getting head is half. Okay, so this represents the probability of getting head. Okay, getting head is half. Similarly, we can get a probability of getting tail is also half. Okay, so here this represents the symbol. This symbol represents the probability of getting tail. Okay, so this is the case for just coin one. Instead of taking one coin, we can take two coins. Okay, so for two coins, if you flip at the same time, okay, then you can get total outcomes, say, or we can say total states will be 4. So it could be 4 states like this. Both we are getting head, or we can get both tail. Okay, and we can get head and tail. Head in first coin and tail in second coin. We can get tail and head. Okay, these are the possibilities of getting. So we can find, for example, what is the probability of getting head. Okay, so this will be equals to 1/4. Okay, so similarly, we can keep going like this. We can keep going like this. So, for example, if we want to find what is the probability of getting one head and tail, okay, we can say one head and tail So these are the two possible, head and tail and head. So this is the 2/4. So in this case, we are taking the 2 points. Similarly, if you are continuing like this, for example, for 3 coins, you can say like we have, if you had 3 coins, the total outcomes will be 8. So how we know these two, it has head and tail. So we are repeating for 3 coins. So that's how we get it, this number 8. Okay. So for example, we can get head kind of thing. Okay, head and tail, or we can get head. Total number of outcome will go like this. Okay. So this means if we keep repeating by the for coin, if you have say the 80 coins or 100 coins or 200 coins, okay, what will happen that the outcomes will be 2 over, for 80 coins it will be 80. Okay, so you have to find accordingly. So this is the outcomes, total outcomes from this scenario. So the same thing will happen in the case of if you take the gas molecules. In the case of the gas molecules, so these are called the state. Okay, these are called the states. For if we talk about for gas molecules, we have similar scenario. So this means we have say state P, and T. This is called the macro state. This is called the macro state. And under this we have we have many outcomes, just like this. Many outcomes. So under this we have many outcomes. These are called the micro state. Okay, these are called the micro state. Okay, based on that, there is one equation based on these outcomes. We can say that the absolute value of entropy will be K times log omega. So this basically comes from it's called the statistical physics. So this represents the absolute value of entropy. Okay, and K, K is it's called the Boltzmann constant. And here, the important part, omega is the states. Okay, this is the states. For a given macro state. For a given macro state, it has a number of the macro state. So we use this equation to find the entropy, to find the absolute value of the entropy. Okay, so in this way, we can say that most probable macro state is one with the greater number of micro states. Okay, so macro states. So for example, if you consider the 2 points here, these 2 states, these are the most probable, okay, probable state. So we can interpret the entropy in this way. So these are the further resources you can look at for this chapter. These are the very good videos. You can go over that. Okay.